OK， 我们开始上课。So after the introduction to post-measurement, we can focus on the first post-measurement technique, the field autocorrelation, with the abbreviation FA. There are three sections in this part, starting with linear self-gating. It's the basic idea of FA measurement. We will talk about the limitation and the practical issues of field autocorrelation measurements. Then another variety of field autocorrelation, which is field cross-correlation. So what is self-gating? Because as we have known from the previous section, if you have an even faster gate, you can always measure fast signal. However, if you have no faster gate, why not just let the pulse get itself? Okay. 我们在前一个 section 有提到一般物理上你要做量测，你的讯号很快，那你通常需要一个更快的这个 gate signal 来做取样。但是如果你已经没有更快的 gate 可以用，那 at best what we can do is let the signal pulse itself for gating. In practice, this is not difficult because you can always build a microsync interferometer to achieve this purpose. This is the schematic diagram of microsync interferometer. Say the red one is the input pulse. BS is the first beam splitter. So input pulse is split into two different passes. And they are recombined at the second beam splitter. And you can place a slow point detector to measure the output signal. Here, the slow means the response speed of the detector is much slower than the pulse width. Okay? Then what happens? Say we model the electric field of the input pulse, okay, the red one as E sub in of t, which is real part of A of t times the carrier e to the j omega 0 t. Apparently, A of t means the envelope function, and it is a complex function in general. After passing through the microsync interferometer, we might have something like this, a pulse pair, where there is a time delay tau between the two pulse replicas. And the delay tau is controllable by this translation stage. If you increase the beam path of the translation stage, you can increase the relative delay tau. Okay? Mathematically, what is the electric field of the pulse pair? Okay? It's not difficult. Now it's proportional to E sub in of t plus E sub in of t minus tau. Okay? Maybe the first one is proportional to the input field. And the second one is proportional to the input field with a time delay tau. So mathematically, it's E sub in of t minus tau. Okay? But in analysis, we prefer to work with the envelope function A of t. So what is the corresponding envelope for the pulse pair? Okay, that's the critical issue. It turns out that the envelope function of the pulse pair is proportional to A of t, the original envelope function, plus A of t minus tau the shifted version of the original envelope function, but there is an extra term, e to the minus j omega 0 tau. Okay, so don't forget about this term. It's very critical. But can you figure out why there is an extra term here? Remember, we can start with the earlier equation, okay? The electric field of the pulse pair we have known. How to extract the corresponding envelope function from the field? You just look at the carrier envelope representation, right? This is envelope. You have to multiply with a carrier, then taking real part, you got the electric field. Now, you have the electric field already. What is the corresponding envelope? Of course, it should be the envelope of this one plus the envelope of this one. The envelope of E sub in of t, according to the definition, is of course A of t. No problem. But what is the envelope of this one? Okay, so you can replace t by t minus tau, right? So A of t minus tau times e to the j omega 0 t is replaced by t minus tau. Okay, but when you talk about the envelope, you just extract the carrier e to the j omega 0 t, and there is a remaining term here. Okay, e to the minus j omega 0 tau. So this is a very important term. But as I mentioned, we can only have a slow point detector to measure the output pulse pair, right? So we have to calculate the laser power first. P means laser power. It's proportional to the absolute square of the envelope function, A sub out of t and the tau, right? But can this slow point detector directly measure this function? Can it do that? No, because what is the time square of the power? It's still very fast, right? It means you have to measure the pulse pair envelope function, which is in the femtosecond scale. It's far beyond the response speed of this slow point detector. So it cannot tell this function. But what can the slow point detector measure? 你量不到这个双脉冲的包络，你量到什么？ It's slow, so what can you measure? Remember when we introduce the laser power or laser intensity, there are 3 different types. Instantaneous power, right? Envelope power and average power, right? So what is the number? What is the physical quantity the slow point detector can actually measure? The instantaneous one or the envelope one? Neither, right? It can only measure the average power or pulse energy. So that's it. The point detector only gives you the integration of the laser power. The integration is carried out with respect to variable t, right? Remember, tau could be a fixed constant when the stage is fixed at some position. Then you get an average power, which is a number only. Then you have to scan the delay tau. For each delay tau, you got a different number. Eventually, you got a one-dimensional trace, which is something like this, okay? Horizontal axis is delay axis. Center at 0 delay, you got the maximum signal. When you gradually scan the delay, you got different average powers. So point by point, you got a one-dimensional trace like this. And it's denoted by I sub FA. FA means field autocorrelation, as we will introduce, as a function of delay tau. Okay? So experimentally, this is what you can get. The remaining question is, what information can we retrieve by analyzing this data, this one-dimensional trace? Okay. Any question? Okay. So now, mathematical analysis, field autocorrelation trace. The raw data trace can be formulated in this way. The field autocorrelation trace as a function of delay tau, as indicated in the last page, is the integration of the envelope power, or with another symbol, the bracket symbol. 你看到这个就是时间积分的意思。Okay. Then you just substitute the formulas. Okay, here, here, here. Okay, 就用这三个地方哈。你要做积分，你的 integrand 就是来自它。那你这个东西又来自第二个 equation 哦，只是连续把它带入就可以了。Then you can prove it's proportional to constant 1 plus real part of a new function g sub 1 of tau times e to the j omega 0 tau. Okay, remember at this point there is no variable t because of the integration. Okay, after the integration, variable, only tau variable. So g1 of tau, e to the j omega 0 tau. Okay. So that's it. But we know if g1 is a complex function, you can rewrite real part of a complex function by in this format. Okay, which is g1 tau absolute value, the magnitude function, times cosine of omega 0 tau plus the phase of g1 function. Is it okay for you? 你取10步，那就是把绝对值提出来，它的相位会跟这一项合并，那 real part 所以会变成 cosine function. And this is a real function. Of course, because this is your raw data trace, the physical quantity you can measure is always real. So this function has to be real function. Although g1 function could be a complex function. Okay. The question is, what is g1 function? Okay. It's defined here. You see bracket again, so it means time average. What average? The envelope function a of t times a of t minus tau complex conjugate. Remember, a of t is the temporal envelope function. It is, in general, complex function. Magnitude and the phase. Okay? So complex function multiplied with the same function, but with two modifications, a time delay and a complex conjugate. And the zero product with time average. It's a field autocorrelation function. But in our definition, it's normalized to tau equals 0. When tau equals 0, you have a times a star, which is a absolute square. It's in the denominator for the purpose of normalization. And since this is a complex function, so you can rewrite it as the product of magnitude function times e to the j of phase function. Okay. So this is something here in the formula. And officially, this is the normalized field autocorrelation function of the complex temporal envelope function a of t. 它就是 g1 函数就是小 a 函数的 这个 normalized field autocorrelation function. Okay. And you can figure out why the name is field autocorrelation. First, why it is about field. You can see it's about A of t, which is a complex function, not just the or magnitude function. Okay? So that's why the name is field. The second term is autocorrelation. Why it is called autocorrelation? It's very similar to what you have studied in probability theory, right? 自己乘上自己的平移量 ，OK？ 那这个叫做自相关嘛，啊，当 τ 等于0的时候，就自己乘自己，啊，那就得到绝对值平方，这应该是最大的情况，数字最大的情况。Whenever tau is increased, you can imagine the two functions are gradually decoupled, right? When tau equals 0, they are perfectly overlapped. So the correlation is maximized. When A is larger, the two functions gradually separated, then their product is nearly 0, right? When they are totally separated. At that time, the correlation is almost 0. So you can imagine G1 function is maybe a bell-shaped function. Peak at tau equals 0, and the decay to the background or 0, the delay tau is much larger than the width of the A function, A of t. Okay, so you can roughly imagine what does it look like. Okay, one example. I have assumed a transform limited pulse with two small side lobes. So this is not a very beautiful pulse shape. You have a main peak, but you have two side peaks as well. And this is the intensity function in the time domain. Okay. Then computer simulation shows the field autocorrelation trace of this function looks like this. Okay, you see dense fringes, and roughly speaking, you can see a main peak and the two side lobes as well, right? But of course, the shapes are still different. But you can see some clues about the original pulse shape by way of the field autocorrelation trace. And the peak to background contrast, this is peak, right? This is background. When delay is very large, the signal will stay here. And I normalized the trace to the background, and you can see it's 2 to 1. Okay, in theory, it's 2 to 1. So this is something you can use to estimate, is there any problem about your experimental setup if it is no longer 2 to 1? Something is happening. Okay. However, the shape of G1 tau absolute value, I use a blue solid curve to illustrate G1 absolute value. It's very different from that of I of t. Okay, so simply speaking, even you can know the magnitude function of field autocorrelation function, G1 absolute value. You can know the blue curve, but the blue curve is still not the original pulse shape I of t. They are different. Okay. So simply speaking, there is something else to do to really retrieve the shape of I of t. Field autocorrelation measurement is insufficient to do that. Okay. Any question? 好，所以我这一页强调的是，我随便拿了一个 pulse shape， 它不是一个简单的 Gaussian 或 second hyperbolic function， 然后我可以得到一个 field autocorrelation trace。它的长相似乎暗示了原来的脉冲形状，可是也不完全对，所以还有一些 extra work 必须完成，才可以知道真正的 pulse shape。And usually we define the full width at Helm maxima of the G1 absolute value function by the correlation width delta tau。所以它不叫 pulse width delta t， 它叫 correlation width delta tau。And usually delta t and delta tau might have certain ratio, fixed ratio, if the shape is known in advance. But here I just define, this is so-called correlation width of the measurement. One question, okay? You see, in our measurement, the detector will give you different average power, sometimes very big, sometimes almost zero, right? And does the tau-dependent average power violate the energy conservation? Of course not, but why?
它画出来的话，它不是会越高。叠在一起，就是 Hall average， 然后乘以它的时间，会是定值。
Let's go back to the setup. Okay, here. I place a detector here to measure the average power, and it's up and down, change with delay. But in theory, physics does not allow us to violate energy conservation, okay? The same in purpose, why can I see tau-dependent average power? 有时候几乎没有量到 power， 有时候量到 power 很大，可是我灌进来的 power 是固定的。你不要忘了，我这是 slow detector， 我不能去追踪这个 pulse shape。
我是说两个叠在一起的次数总时间。
哪两个叠在一起？
那个 first pair。
嘿，怎样？
就是他们所占据的时间，总共的时间。
一定在我的积分时间范围内。这整个全部把它送进去积分嘛，我去积它的总面积，这就是我量到的。有时候大，有时候小，这不会很奇怪吗？我没有漏掉，我不是只有积一部分的时间，那有时候大，有时候小是正常的。不管 delay 多大，我都会把整个 pulse pair 的 total power 给量进去。但这样我还是量到有大有小，没有违反能量守恒。Of course, this is about interference, but how to justify there is no violation about energy conservation? Good. 当我量到很弱的讯号，就代表另外一个地方有很强的讯号。另外一个地方在哪里？ How many output ports can I have from this microsensor interferometer? I can have 2 ports, not just 1. The other one is here. I just skip the, otherwise there is another path here. If you place another detector here, you can get another trace. And if you sum up them together, you can get a constant. So there is no violation of energy conservation. The only issue is you simply measure one of the 2 output ports. That's it. And you can see interference. Constructive, then the other one is destructive. The sum is a constant. Okay. Good. But what we can directly measure is a data a fringe, a trace with fringes. How could we retrieve a complex function, G1 function, from a real trace? It looks interesting at the first glance, right? 我的 data 是这个，可是这是一个实数函数，我怎么从这个实数函数里面抓出一个复数函数出来？所以这有一点点的 signal processing 必须做。So there are several steps you can do that. Step 1, perform Fourier transform for the data trace. Okay, so let's see what is the formula of data trace. In the previous slides, we have seen it's proportional to constant 1 plus real part of G1 times the carrier. That is the formula. But you can also rewrite this one as the same constant 1, but real part of a complex function is rewritten as 1/2 times the complex function plus 1/2 times the complex conjugate of the complex function, right? So with complex conjugate, you have G1 becoming G1 star, e to the j omega 0 tau becoming e to the minus j omega 0 tau because of the complex conjugate. Okay. Then after Fourier transform, okay, so we take Fourier transform for the data trace, and by definition it's integral of the data trace times the kernel function of the Fourier transform. Here I use another symbol kappa to denote the counterpart variable of tau. Okay? Traditionally, after Fourier transform, function of t becomes function of omega. T and omega are a pair of variables. But here I have tau, which is different from t, so I use another symbol kappa. Tau and the kappa are a pair of variables, just like t and omega are a pair of variables. So this is only definition. Your input function times the kernel function performing integral for the original variable tau. You got the Fourier transform. Okay? Then what happens if the integrand IFA of tau is this one? You see 3 terms, right? So the first term, constant 1, after Fourier transform is delta function, as you have known, delta of kappa. 1/2 is preserved. G1 times carrier after Fourier transform. You can apply the Fourier transform property, right? After transform, this term contributes to a shift in the frequency domain. The amount of shift is omega 0, the carrier frequency. So G1 after transform becoming G1 tilt. So I use a simple tilt to illustrate it's in the frequency domain. Okay? Originally, it's just the G1 tilt of kappa, but because of the carrier term, it becomes G1 tilt of kappa minus omega 0, a shift of omega 0. For the same reason, the third term, you got this. G1 tilt star of minus kappa minus omega 0. So this is a term centered at omega 0. This is a term centered at minus omega 0. Okay? How about this? Center at 0. It's DC term, right? So you have 3 well-separated components after Fourier transform. Okay. And here is the reinstatement. Kappa is the delay angular frequency. Okay. Angular frequency is symbolized as omega, but it comes from the variable delay tau, so it's called delay angular frequency. And the definition of G1 tilt function is Fourier transform of G1. Okay. So this is step one, performing Fourier transform.